Hello, my name is Mark, and today we'll be doing some adiabatic flame temperature of a steady state system. So here, what we're going to do first is I'm just going to draw the system, help explain it a little bit. Okay, so we have the system here. We have, let me give them some room there. So we have the air going in along with some fuel. Air and fuel. And then what we have out is going to be like the flame or a hot gas. And then so we know that the temperature going in, we're going to make that 298 kelvins, and then the temperature out, T out, T, that we'll need to find, so we don't know that yet. We'll put a question mark there. So now let's get down to the equations. So I'm going to use the energy equation, so the change in mass, actually, so we know that it's a steady state and it's adiabatic, so that means the mass in equals the mass out. So that'll help us with this equation that I'm going to write down. So we got change in mass, enthalpy plus kinetic energy plus potential energy divided by change in time equals change in mass times enthalpy times kinetic energy times potential energy. And then that will be times the N minus dt. And so, like I said, since we know that's a steady state and that it's adiabatic, we can kind of cross out the kinetic energies and potential energies, that, and the mass. So what we're left with is, zero equals E in minus E out. Let me erase that. And then that means like E out equals E in. And that's going to be one of our nice equations that we're going to use. So yeah. Now, we're going to be using the heat capacity too. So, we'll say heat capacity equals H. So, we'll say H T F equals H 298 kelvins times F plus the integral T 298 Cp dt. Alrighty. Now, for the sake of convenience, I'm just gonna write down and tell you guys the ChemCAD equation that we will be using. So it's gonna be ChemCAD equation 107. Okay. And now let me try to remember that equation real quick. So we have 1 equals A plus B so y equals a plus b. Then we have c over t over sine h c over t squared plus d e over t cosine h e over t squared. Okay. Alright. Now, so basically what I'm going to do is I'm going to use Wolfram alpha to help me solve this. So I will be right back. Alrighty, so with the equations that I got from Wolfram alpha, or the solutions I got from Wolfram alpha, we get for this one, we get equals c o t h c over t plus a constant. For this one we get negative e tan h e over t plus a constant. And this will be used in our, this will be very helpful in our coding, these two equations. Alright, I'll be back for the second. Alrighty, so now what we're going to do is stoichiometry and balancing the equations of the fuel. So what we're going to do is we have CH4, C2H6, and C3H8. And so what we're going to do is we're going to add in the oxygen because the fire needs oxygen to feed itself along with the fuel. So we need oxygen, and it's going to be air too. It's not pure oxygen, so I'm going to add in nitrogen to that too. So we have CH plus O2 plus N2. O2 plus N2 plus O2 plus N2. That was a very ugly 2. Let me redo that. Okay. So, and then we'll say each of those equals. I wish there was a way that I can make the page bigger. Let me rewrite this, okay? Just so I have a lot more room. Okay. So we have 4 C2H6 and C3H8. Then we're gonna add oxygen and nitrogen. Okay. Oxygen and nitrogen. And the reason why I'm leaving spaces here is to help when I'm balancing. That way I don't need to like erase it or do anything like that, you know. Keeps it nice and cleaner. And 2. And then you will say those result in CO2 for all of them, and H2O and nitrogen. So plus H2O plus H2O plus H2O. Alright, so there's our equation right there. That looks beautiful. Okay, so we also need to remember, this is going to be like a little future type thing, that we want the ratio between nitrogen and oxygen to be 79 to 21. Okay, so let me balance these out real quick. So we're going to need 4H2O. So that would be a 2 there, which will give us a 2 here and 2 here. Just to help with our proportion. So we don't need to change the proportion, we just need to change the coefficient in front of the N to equal oxygen. So then we also need to do the same 9 over 21, same 9, just looks like a 2. 79 over 21. Okay, there we go. Okay, let's balance a little bit more. So we have 2 there. We're going to need a 3 there, and then we'll need a fraction, 7 over 4. 7 over 4 and 7 over 4 for the N value, just so that, again, it equals the oxygen. So we get 79 over 21 and 79 over 21. Alrighty. Now on for the next one, what we'll do is need 3 carbon, and then 4, not 4, need 8, yep, that's right. We have 4 oxygen, 6 ox. So, yeah, 4, 5, 6. So we need no, sorry, 6 plus 4. So we have 10, so we need 5. There we go. And then 5, 5. Then we need the same 9 over 21. Same 9 over 21. And that will be our stoichiometric equations there. This is what we'll code into Colab there, along with these. So we need that, and we need this. Alrighty, thank you for watching. I'll be back with the code in a second. Alrighty, welcome back. Now I'm going to be coding the equations that we got previously. So to make things a little bit easier and like less space, make things shorter, I already typed out the link for GitHub. This will give us all the properties, the tools that we need to help solve this. You could see in here too. You got the data of all the gases, and then we also have the tools too. So we import the tools, we optimize SciPy and import NumPy. And then for this line, we have P for properties equals, and then we just have a nice array of all the gases that we need and all the materials that we need. So methane, ethane, oxygen, water, and propane is the like kind of link there for the tool. So let's use N-propane, nitrogen, and carbon dioxide. Now what we're gonna do is, so we ran that. Okay. So now what we're gonna do is going to help list all the variables and the equations. So the fuel ratio equals, and this will be like 1 for like the what's it called, when we balance that out the equation. This is the ratio between the two, carbon and hydrogen. So yeah, we need to make an array. 1, 4, and then another. Sorry, I'm looking at my keyboard. I'm not used to using brackets as much. 2, 6, I think it was. And then 3, 8. Yep, that looks right. Alrighty. Then we also do like the fuel equals NP. Need to do an array. Make it an array. 10, 1.5, and 1. Alrighty, now let's do CH equals, okay, CH, and then this will be the multiplying the two arrays together. NP dot, oh, that's for that one. We will do fuel time matrices, multiplication with matrices, so we use the at symbol, times fuel ratio. Oh, didn't mean to run it, but it doesn't really matter. We'll still do, now we need to do the CO2 equals, and C, we do the H2O equals H lava 2. Do nope, that's not O. O2 equals C plus H2O, no, divided by 2. There we go. And we need one last one, N2 equals, and then this will be the ratio with oxygen, say 9 over 21 times O2. Alrighty. Stretch. Yeah, that should be good. I'll come back to it later if it's a little messed up, but as of now that should help. Feed equals, so this is like the going in, you could say in, feed, whatever, np dot concatenate parentheses, bracket, fuel, np dot array, and then this will be listing everything we do. Two comma and 2 comma, and then those are going to be initial 0 and 0. There we go. And then we also need one for the product, product equals np dot concate. I think I spelled that right. Did I? Yeah. And then do np dot zeros underscore like fuel comma np dot array and then this one will be comma and 2 comma OCO2 comma H2 0. Yep. I'm just checking it, make sure we have everything. Yeah. Sorry, H2O. I think I just hit shift on that there and it made a parentheses. There we go. Run that, make sure it reads everything properly. Alrighty. Now what we're gonna do is define delta HSIG, the product equals, no, just T. And then this will be our like main equation where we plug everything in. Let's do colon. That's why I needed. I wanted the indentation there. Okay, return. And we get P dot C P I G A times T, and then plus. Okay, so we have P C P I G A times T plus, and then P dot CPIGB times P dot CPIGC divided by np dot tan H. And this is our equation from when we did the integral in Wolfram alpha. It's just a little, it looks a little special. little different. Just to help with the coding. Tan H, and then we do P dot CP IGC divided by T. There we go. Alrighty. And we also have another long one. Minus P dot CPIG D times CPIG D times P dot CPIG E times NP dot tan H and H P dot P dot C P I G E divided by T. All of that divided by 1000, because in the we divided by 1000 because in the file it's listed as like kilomoles, so we need to make sure that it's all the right unit. Okay. Then we also need this one. And then this is the energy balance. And then, oh no, shoot. Sorry, this is the, nope, NT. And then, let's see if I get the indentation, there we go. T equals, the energy balance is next. And then we want that to start at 0, indexing it. We hit the delete space there. Okay. Then we also need, okay, so NT, and we return it. MP dot N comma P H F I G P dot, that would have given us an error, and close parentheses plus P dot N comma delta H S I G T minus delta H S I G, and then this will be 298 because it's the it'll be 298 because that's like the starting temperature when it goes into the system. Yep. Alrighty, now for the next one, which I kind of alluded to already, and that's the energy balance. So we do EF underscore we'll call that EB. Oh, I forgot the colon. There we go. And then T equals EB array at 0, or index at 0. Return feed, comma, 298. And we're going to subtract that from the product. Okay. Yep, because of the 0 there. Alrighty. We're golden. Then, I'm going to leave that space. Then, last but not least, we need to use the root to give us an answer. So, root energy underscore balance, comma, 298. And then we run it. Oh, I see. So this will be capital C. Run that, run that, run that, run that. Fan H. Some typos in here. Just gonna run everything. And that does not look right. Let me run through all these here. Let me see. Gonna read through it, make sure I have all the parentheses in the right places. Might add some spaces here just to help organize it more or better. Let's see. Make sure that there's nothing wrong with these. Alrighty, I'm back, and I think I figured out the problem when I first started out. I think I might have had the gases and like the substances in the wrong order. So I'm gonna retry that and see if that helps. Methane. I'm not sure if it will or not, but that's my best guess. And propane. Then we have oxygen. And nitrogen. let's run that and see. Okay, yes. This is what it should look like. The other one, so this is going to be our final temperature there in this that comes out of the system. The other one was just too low, 534. Yes, it's like bigger than 278 or 298, but it is still too low in my opinion. So this one is looking a lot better. Um, yeah, thank you for watching. Hopefully I'll be able to do more in the future.